Okay, so welcome back. In the last lecture, we talked about the Eulerian graph, and at the final part, I talked briefly about directed graph, but I think there is a problem there. So let me be more precise and repeat. So for directed graph, for example, if I assume D equals VA is a directed graph, then there is a property called strongly connectedness. So it is strongly connected if for any pair of vertices, for example x and y, there is a directed path from x to y. So this property is kind of important. If we are trying to find a Euler tour or Euler path in a digraph, the digraph has to satisfy this property in the first place. So it means that you have to be able to move from every point to another point. So the pair of points x and y are chosen arbitrarily. If you cannot, for example, move from one point x to another point y, there's no way you can find something like a Euler tour. Okay, so after this definition, I have this theorem saying that a digraph, actually a strongly connected digraph. You have to assume this a strongly connected digraph admits Euler tour, a directed Euler tour. If and only if for every vertex x, for example, the in degree of x, the out degree of x equals the in degree of x. I put this as the last problem in your list. So because the proof is very similar to the proof of the undirected graph. It's basically a kind of induction. So you follow the path. Every time you enter a vertex, you have to be able to leave it because of this condition. So every time you arrive at a vertex, you are able to leave it as well. So you follow the path, you follow the trail. Eventually, you will find a closed trail. However, this closed trail, for example, you start from x and then you follow the direction and you find a closed trail. After you find a closed trail, delete it. There will be several connected components, and each one of them is a directed graph with the same condition but with smaller sizes. You have to use induction. And for example, after you delete this closed trail in some connected component, you use induction to find another Euler tour for it. And then you do this for all the connected components. In the end, you can connect all these things to become one single closed trail, and it visits all the edges. Okay, so this is a brief description of the proof of the last problem in your list. Okay, so today we will talk about something different, and it looks very similar. So lecture 4, we talk about Hamiltonian paths and cycles. So the purpose now is different. We are trying to find a cycle. This time it's a cycle. You're not allowed to repeat vertices or edges. So you're not. So you are trying to find a path or a cycle which visit all the vertices instead of edges. Okay, so given a graph G, so we ask whether or not there exists a cycle or a path. So it's two different questions, but it's okay. So let's only write one. A cycle which passes through every vertex. So you can ask a similar question about the path. So if you have, then you call, if you have such a cycle, you call this cycle a Hamiltonian cycle. And if you have such a path, you call this a Hamiltonian path. In the literature, some people call it Hamilton, simply Hamilton cycle, Hamilton path. But half the people use this language and half the people use the other one. So we follow Hamiltonian paths and Hamiltonian cycles. So difference, like I explained, there are similarities, but difference is that we are focusing on vertices. And if you have such a cycle, it's not necessarily your cycle will cover all the edges. It's not possible in general. And this actually the results are quite different. The situation about Hamiltonian cycle and Hamiltonian path are not very satisfactory. There are some conditions, but there are questions that are difficult to answer. So it's not completely clear the conditions we know now are good enough. So for example, we know some set of conditions. Today we will prove some kind of some set of conditions will imply that the graph meets a Hamiltonian cycle, but you don't know if this set of conditions are really necessary. Okay, so maybe the conditions are too much. You don't know. Okay, usually let me make a comment. There are a lot of conditions. Today we will prove some, and there are a lot of conditions. So basically, usually the conditions are like if your graph have enough. So usually it's like this: if the graph has many edges, then somehow it contains a Hamiltonian cycle. Okay? So like I said, there is no exact condition for the existence of a Hamiltonian cycle. So today we are trying to prove the following theorem. And actually we are going to prove something a little bit stronger than this. So this belongs to Dirac. So we call it Dirac's theorem. And it says if the degree of every vertex is at least half of the number of total vertices of the graph. So if dv is at least half of n for each v, for every vertex v, then g admits a Hamiltonian cycle. We are going to prove something a little stronger than this, and in practice is kind of interesting. It's kind of interesting of its own right. So usually this is called all condition. So there are many similar theorems. They put similar conditions. So there are huge amount of theorems in extremal graph theory. For example, existence of matchings and something similar like this. And whenever people put this kind of condition, they call this condition all condition. So what condition? So for any, the G has at least 3 vertices. Suppose any 2 vertices, x, y, non-adjacent, but they are not joined by an edge. This xy is a non-edge. For any non-edge xy, we assume that the degree sum of dx plus dy is at least n. Then G admits a Hamiltonian cycle. Okay, it is pretty clear that this is stronger than Dirac. Because if a graph G satisfies this condition, first of all, you can pick a pair xy, which is non-adjacent. Otherwise, their graph is a complete graph. So you are able to choose at least 2 vertices that are non-adjacent. And then you know that the degree sum of them is greater or equal than n, because you assume that I'm trying to prove Dirac using all. I'm assuming this condition. So this condition clearly satisfies this condition. Okay? So a comment is that remark, all condition implies, so this theorem of all implies theorem of Dirac. And this is an exercise. You can follow what I just said. It's pretty simple. So the proof of theorem of all involves a technique is very important. So this kind of technique is it's not difficult, but it's very important. Even in modern research about finding Hamiltonian cycles in random graphs on all kinds of different settings, this technique is fundamental. So let me try to prove this theorem. Theorem of all. Okay, so suppose not true. Then, okay, here is another technique in graph theory. So if the statement is not true, then we can pick an example which is a counterexample. So let's say an example with n vertices which does not satisfy the conclusion of this theorem. So of course it satisfies the condition and does not satisfy the conclusion of the theorem. And here there's a clever trick. So we can also choose such example to be be maximum. In the sense that if one adds one more edge to it, then the conclusion will hold. So in the sense that if one adds one more edge to G, then it admits a Hamiltonian cycle. Okay, we can do this because we know that the complete graph obviously has a Hamiltonian cycle. So if you keep adding edges, at some point you have nowhere to put the edge. Then we can choose the example, since we suppose in general this is not true, so we can choose the example that is maximal in this sense. So it has a maximum number of edges. Okay, so locally you cannot add another edge such that the graph also satisfies all the conditions and does not admit a Hamiltonian cycle. So, but if you think about it carefully, it means that. So, for example, you add one more edge, you call it E, then the graph admits a Hamiltonian cycle. Then this Hamiltonian cycle, it must contain this edge E. Let me write everything down. So cycle. For example, E. So it means that G plus E admits some cycle, some Hamiltonian cycle, and which contains the edge E. So this cycle must contain the edge E. Otherwise, this cycle belongs to G itself. Okay? So then it follows, if you take E out again, take out E again. So it follows in the original G, there is a Hamiltonian path. Let's write it as V1, V2, V3. Okay? So it will this path will visit all the vertices. So this is Vn minus 1. This is Vn. Okay, so this, for example, is the edge E. We put it in and take it out. Okay, so we don't see it again because this edge does not belong to G. Okay, so this is all the vertices, and we name them with this order with respect to this Hamiltonian path. Okay. So by the condition of all, we know that the degree of V1 plus the degree of Vn is at least n. Okay. So here, if you stare at this picture and you look at this condition, I have this claim. We can prove that there exists some vi such that v1 vi and vi minus 1 vn are both edges, in G. So what happens is that my claim is that, okay, this is my path, and there is a vi here, and for example, this is a vi minus 1, and then this is an edge in G, and this is also an edge in G. This is my claim. So let's see how the claim already implies our theorem. So let's see, claim implies theorem. So where is the Hamiltonian cycle? So here, let's draw it many times. So here you have v1, v2, and some place you arrive at vi minus 1, and here is vi, and you continue, you arrive at vn minus 1, and here is vn. Okay, suppose we know that v1 and vi has an edge, and vi minus 1 vn has an edge. Now where is the cycle? So it's pretty clear, right? So let me write v1, v2, etc. until vi minus 1, and then you move here directly to vn because this is an edge, and then you move backward, so then vn minus 1 until vi. But v1 is an edge, and you come back. So this is Hamiltonian cycle. Okay? So it remains for us to prove the claim. The claim is also not difficult. You really you just need, let me try to prove the claim just right here. So let me try to prove the claim on the right side of this, because I need this condition and I need to look at this picture. Okay, for example, let's write vi1, vi2 until vik to be the neighbors of v1. So v1 has dv1 neighbors. Okay, so let's say this number is k. Let's say k equals dv1, and I know that dvn, the last vertex vn, has neighbors at least n minus k. Okay, so let's put names. So k is the number of neighbors, so it's the degree of v1, and we have more names. I put vi1, vi2 until vik as all the neighbors of v1. Okay, so we know that for example, i1 minus 1, vi2 minus 1, vik minus 1, these k vertices are distinct, but possibly this guy is v1, and we know that v1 and vn has no edge. But anyway, these k vertices are distinct, and in particular these vertices. So if you ignore the first one, because it possibly equals v1, so the rest, the remaining are k minus 1 distinct vertices. Okay, and we are trying to prove that one of them must join an edge to vn. Suppose not. Suppose none of them has an edge to Vn. So what are other choices for the neighbor of Vn? There are not many. So we know that V1 is not a neighbor of Vn. And all these k minus 1 distinct vertices are not neighbors of Vn. So it means that degree of Vn is at most, so there are at most n minus 1 choices because it does not join itself, and then minus k, which is n minus k minus 1. And this is a contradiction because dVn, so here it implies dVn is at least n minus k. And here we prove that dVn is at most n minus k minus 1, which is a contradiction. Okay? So this proves the claim, and the claim proves the theorem. Okay? So this is a short video for the first part of today. And when we meet, we will discuss some more variation of these techniques and also some applications. Okay, let's take some minutes.